remember p hat is x over n. The mean of that is p. Your standard deviation is the square root of p times 1 minus p over n. The criteria, we never really did a simple random sample. That was always the case. But criteria is the same, n times p times 1 minus p. It has to be greater than or equal to 10. And it has to be independent, which means the sample is less than 5% of the total population. So that's everything we've already said about p. Nothing new. Still the case. In our hypothesis testing, we are going to be checking if things are significant. Significant is unlikely under the assumption that the null hypothesis is true. Remember, we talked about null and alternative hypothesis today, or yesterday. So what we're doing is basically finding the probability that the alternative hypothesis happens if the null hypothesis was true. Okay, so if, like, for instance, my null hypothesis is that p is 0.1, and my alternative is that p is less than 0.1. Okay, so if I work this out and get the probability that p hat is less than 0.1, let's say it turns out to be 0.15. That means if the null hypothesis is true, there is a 15% chance that in my sample, my p was less than 0.1. Is that unusual? No. So that would not be evidence that my alternative, or that I should reject my null hypothesis. Even if the null hypothesis is true, that's not uncommon. But if I got it to be like let's say 0.0015. That means if the null hypothesis was true, there is a less than 1% chance that this happened. Is that unusual? Yes, that would be extremely unusual, which would lead me to believe that that null hypothesis really wasn't true. Okay, so we are working under the assumption that the null is true, finding the probability of the alternative, and seeing if that's unusual or not. There are two different approaches, and we just need to kind of decide something as a class here, I think. There's a classical approach and there's a p-value approach. I can show you both methods. But I think it is, in general, confusing to go back and forth between two different methods when solving problems. So I don't want to, not show you something, but I also don't want to confuse you by switching methods over and over again. So I'm going to tell you about the classical approach. I'll do maybe one problem with it, and then I'm probably going to stick with the other approach for the majority. On the homework, I think maybe one question I'll ask you to do this approach, but then everything else will just stick with the second approach, and test or quiz, I would just do the second approach. Okay, so I'm going to show it to you because I don't just want to skip something, but technically you could do either one. I just think the other one's easier. So that's how I will most of the time do it, unless you guys just really favor one. So classical approach is all based on standard deviations. Remember, we know our empirical rule. If we have a normal distribution, then we expect how much within one standard deviation of the mean? 68% of the data is within one standard deviation. How much within two standard deviations? 95%. Now, once you get to that threshold, that means there's only 5% left over, right? So there's only 2.5% on each side. So basically anything more than 2 standard deviations is going to be unusual, a less than 5%. So it's basically finding how many standard deviations from the mean are you? If it's more than 2, it's probably unusual. All right, so if we look at this one, a researcher obtains a random sample of 1,000 people and finds that 534 are in favor of banning a cell phone while driving. So that's our p-hat, 534 over 1,000. Does this suggest that more than 50% of people favor this policy? So let's just stop right there. What would my null hypothesis be? We said yesterday it's always equal, and we're talking about p's on this. So it would be equal to something. What would I be checking?
0.5.
Yes. P is 0.5. My alternative would be that P is more than, so greater than 0.5. Okay, so we have to see, is this, does it suggest more than 50%, or is it possible that the true proportion is somewhere less and we just got an unusual group? So we have to see if this would be significant or not. That's how we would set up our hypothesis. To decide, we have to check our criteria. So is it normal or not? So we have to check our n times p times 1 minus p. So my n was 1,000. My p, that's the p from our null hypothesis. So that's 0.5. 1 minus 0.5. And that's 250. So that's most definitely greater than 10. Would 1,000 be less than 5% of the total population? Yeah. So it's normal, it's independent. Mean. So all the stuff we were doing in our last test. The mean is just our p, so 0.5. Standard deviation is the square root of p times 1 minus p over n. Get 0.0158. So, I'm going to come back to that in a second. We'll reject if it's more than 2 standard deviations from our mean. So first, we need to get our z-score. How do we do a z-score? So what we have, that's like our p hat. In this, what was our p hat? So, 0.534 minus our mean, which was 0.5, divided by our standard deviation, 0.0158. That gives me a z-score of 2.15. Okay, if you think about what this means, a z-score is how many standard deviations from the mean. Right, so this is your mean, this is one standard deviation. Okay, then you would have your 2 standard deviations. If I am 2.15 standard deviations, is that unusual?
Yes.
Yes, because I'm more than those 2 standard deviations. That means when I'm out here, there is a less than 5% chance of that happening by the empirical rule. So, would we reject our null hypothesis?
No.
Yes, because if the null hypothesis is true, this is all based on the probability that the null is true. If the probability, or if the null hypothesis is true, the probability of me finding a sample that I have would be unusual. Right, because it's, if you just think about the empirical rule, there's only a 2.5% chance that you're being out there. So if the null is true, I only have about less than a 2.5% chance of getting the result I have. That's unusual. So that means my null hypothesis is probably not true. So we would reject it. We reject if we're more than 2 standard deviations from the mean. Because that's considered unusual. All right, that's what the classical approach says. I just really don't like this approach. It all relates back to the empirical rule, but I just think it's confusing sometimes. So what I like is what's called the p-value approach. P-value is just straight finding a probability. And I like that better because that's more similar to what we have been doing, right? So we are actually not just going to look at standard deviations, we're going to find the probability of this happening. And I think that's a little more concrete and requires a little less thought on our part. So the p-value approach is just finding the probability of getting that situation. That p-value, just anytime I see p-value, that's the probability of getting one that extreme or more extreme. So in this particular scenario, if we are doing the p-value approach, we would have to find the probability that our p-hat was greater than the 0.534. And isn't that like something you would have had on your last test? Yeah, you get your z-score, which we just did. What did we get? Probability z was greater than 2.15. We know greater than is 1 minus, then you look at your formula sheet. So if I look up 2.15, .9842, and that probability is 0.0158. Okay, I just think this is a little bit easier because is it easier to look at that and say, oh, that's less than 5%, that's unusual. Yeah, and it just relates everything back to what we were doing before.
Can I borrow a formula sheet? I think I left it in the locker.
All right. So our hypothesis testing we talked about yesterday. We can have two-tailed when we have equal and not equal. Left-tailed is less than, right-tailed is greater than. The null is always an equal to. Alternative can be not equal, greater than, or less than. The other thing to note, alpha is the probability of a type 1 error. Depending on the situation, a lot of problems are going to give you an alpha value. The more serious the situation, you'll have a smaller alpha. Okay, if I am, doing a survey to see what if people would like having a food vendor for lunch every Monday. Is that a very serious situation? Is anybody going to die if I make the wrong call on that? No. So I would probably have a fairly high alpha value, maybe even up to 10%, 0.1, because it's not really serious. There's a lot of room for error there. Now, if I am testing a new medication and I want to find the probability that it causes a serious side effect, is that a big deal? Yes. So would you be okay with 10% of the people having a serious side effect? No, so that one you would need a small alpha, like maybe 1%. Okay, so smaller alphas are typically used in those more serious situations. You won't have to decide the alpha value. It would be given to you. The steps for hypothesis testing, so look at this on your notes. It starts out the same no matter what. So the classical approach versus the p-value, in both of them, we start out finding our z. Then in the classical approach, you're basically seeing is your z going to be in this critical region where we would reject the more than 2 standard deviations, and you base it off that. The p-value is the one that I'm really going to use, so you actually find your probability, and this is my favorite part about the p-value approach. It's very straightforward. If p is less than alpha, you reject. So, very cut and dry. The problem has an alpha. If alpha is 10%, and I get my p to be 0.08, would I reject? Yes. Anytime p is less than alpha, you reject. If p is bigger than alpha, you fail to reject. Okay, so I think this one's a little more straightforward. And then we will state our conclusion. You have to make sure at the end you tell me if you reject or fail to reject on those. So let's look at one. Make sure you are taking good notes here because you have to have all the required information. I will be checking for criteria on this. You have to state the null alternative hypothesis. You can't test it if there's no hypothesis there. So, in 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. A 2007 poll of 1,010 adults nationwide, 525 stated they did not trust the media. At the alpha equals 0.05 level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media has increased? So, first, let's check our criteria. Okay, you should always be thinking, is this less than 5% of the total population? So, would 1,010 be less than 5%? Absolutely. Okay, and then the N, 1,010, times P. What P am I using? 0.46 times 1 minus P. You have to verify that that is greater than 10. And it turns out to be 250, so we're good there. All right, you don't have to show me a ton on your criteria, but you have to show me enough that I know you checked it. So now we need our hypothesis, the null. Okay, we're talking about percents, so P is always going to be equal. What was my starting P value? 0.46, the same one we used in our criteria. Does everyone understand where the 0.46 came from? All right, then the alternative. I want to test the claim that the percentage of Americans that do not trust the media has increased. So increased would be greater than 0.46. Okay, so you have to read to know which kind of test you're doing. Now, we just have to get our calculation. We will need our p hat. It didn't state it there. How do you find p hat? Okay. And we get 0.52. Let's go ahead and do 2 decimal places. So we're finding the probability that our p hat is greater than 0.52. Okay, so we do our value, right? We have to convert it into a z. So z is our value, 0.52, minus the mean, which is, I guess, 0.46. I didn't write that out, did I? I should have. Let's go ahead and throw that up here. The mean is the 0.46. Standard deviation would be the square root of 0.46. 1 minus 0.46 over 1010. We get 0.0157. Did everyone get that? Remember doing that on your test. Okay, so far really the only thing we did that we didn't do on the test is write down the hypothesis. The rest of it's what we've been doing. So divided by that. So that's the probability that z is greater than 3.83. All right. What happens if I go to look 3.83 up on my table? It's not even there. Let's go with the closest we can. Greater than is 1 minus. The closest my table goes is 3.49, so that's what I would have to use. And we get 0.0002. So if the null is true, if the proportion is still 46%, the probability that I got a sample of 52% is a less than 0.02% chance. That is not likely, right? So we also have a very cut and dry method. Compare that to alpha. This is smaller than alpha. So what does that tell me? Reject. So since 0.0002 is less than alpha, reject the null hypothesis. Or if I asked you to write a sentence, I won't require a sentence on every one, but if I asked for a sentence, you would say there is evidence to conclude the percent of Americans who don't trust the media has increased.
So fish
So are
sign,
we rejecting the alternative or the no?
Then no.
so fish sign means alpha?
Yes. So yes, we're testing either rejecting or failing to reject the null hypothesis on these. Now, this is something we've done a lot. I'm not going to make you do it by hand every single time, just like everything else we've done. There is a calculator method. So why don't you grab a calculator? On your calculator, we would go to Stat, Tests, and we want number 5, a 1 proportion z test. We're getting a z value, we have 1 proportion. And then it asks us questions. P sub 0, that means the P of the null. So 0.46. X, how many in my sample said they did not trust? N, how many did we talk to? And then you have to tell it, what are we testing? So this one we were testing, so you have to highlight the greater than, P sub 0, and calculate. Draw will draw you a picture of the normal curve with it shaded, so to kind of have that visual. But it tells me my Z is 3.81. Does that look familiar? Yep, ours was off a little bit because we rounded our P hat, but it's close. And most importantly there, it tells us so then once you have that Z, you can look up on your table and get your probabilities from that. Okay, so you can use the calculator for this stuff. Any questions there? So, let's look at another one. When asked, is it more important to protect the right of Americans to own guns or to control gun ownership? 46% of all Americans said protecting the right to own guns is more important. A research center surveyed 1,267 randomly selected Americans with at least a bachelor's degree and found that 559 believed the right to own guns was more important. Does this result suggest the proportion of Americans with at least a bachelor's degree feel differently than the general population? Use alpha equals 0.1. All right, what kinds of things do I need to do here? I can't just do everything on the calculator. We have to write down a little bit. What do I need to check? Criteria. Okay. Would 1,267 be less than 5% of our population?
Yes.
Yes. All right, my N, 1,267. My P was 1 minus P. Is that greater than or equal to 10? So if we check. That comes out to be like 314, so that's bigger than 10, so we're good. So criteria, just the bare minimum here, so I know that you looked at it. Then you have to write your null and alternative hypothesis. Right. My null hypothesis would be what? Null is always equal to. Right. My alternative hypothesis. So alternative, we are testing either not equal, greater than, or less than. We have to look back at the problem. So it tells us, we want to know if they feel differently. Not equal. Okay. So do you guys want to do this one on our calculator? Okay. So if we go to stat, test number 5. P is a null, 0.46. Currently, I really like that number. My x is what this time?
550.
What is my n?
1267.
And we are testing. Okay. So when we do that, it tells me my z is.
Negative 1.34.
Okay. So everybody. Good. Make sure you do that test. Check it. All right. So this one is a little bit tricky because it's not equal. It's a t-test or a two-tailed test. Right. This is my. So we would reject if it's over here or because it's not equal, that's both sides here. Basically, if it's smaller than -1 or bigger than the +1. If we look up that probability, less than -1.34, it tells me 0.0901. That's the probability being on this end. What's the probability of that end? It's, well,
1 minus 5.
yeah, it should be the same, shouldn't it? Because it's symmetric. So you could just take it times 2. So on the two-tailed, basically you look up your probability being less than that number and take it times 2. Your calculator will always give you the negative z here. So if I multiply that, I get 0.1802. That's my probability. What was my alpha level? 0.1. So, is 0.1802 less than 0.1? No. So, since 0.1802 is bigger than alpha, we fail to reject the null hypothesis. Or if I ask for a sentence, there's not enough evidence to conclude that they feel differently.
But it doesn't mean we accepted one.
Right, it doesn't mean I proved it was true, it just meant I can't prove it's false. So I didn't reject the null hypothesis. That means I cannot prove that it is not 0.46. I didn't prove it was still 0.46, I just failed to prove it's not.
So on the last one, we proved that it.
Right, we rejected the null, which means we said there's enough evidence to say it's greater. All right. Other questions? It's not that the math is complicated here, it just gets confusing to think about on these. So we're definitely going to practice this quite a bit. Let's see how much. Okay. We can also use confidence intervals to do this. Again, we're just going to basically use our calculator to set that up. So that would always be an option as well. Let's take a look at this one. A 2009 study found that 34% of teenagers text while driving. A more recent survey found that 353 of 1,200 randomly selected teens had texted while driving. Does this suggest the number has changed since 2009? Use a 95% confidence interval to answer the question. So we have to check our criteria. Is 1,200 less than 5% of the whole population? Yeah. My N, 1,200. What's my P?
0.34.
1 minus 0.34. And that gives me 269, so that's most definitely greater than 10. So far, so good? So then, take a second, read it, and see if you can write down your null and alternative hypothesis. So what'd you use for the null?
P, 0.34.
And the alternative?
P,
Definitely.
So, we could find the probability. This asks me to create a confidence interval. Haven't we already done those on the calculator? So stat, test. Do you remember where we went to get the confidence interval on the last test?
A.
So stat, test,
When do you use A? Use A?
when
or
we're doing
A?
it for X bar. Stat, test, letter A. What is my X? 353. What is my N?
12.
What is my C level? Okay, so if I do that, my confidence interval is 0.26839 to 0.31995. Okay. Look at your null hypothesis. Is 0.34 in this interval? No, I am 95% confident the correct value is in this interval, and it isn't P. So what would I say?
We reject.
So, since 0.34 is not in the interval, reject the null hypothesis. There is evidence to suggest the number has changed since 2009.